What's up everybody? In this video, you are going to code a DeepQ network in Keras, and we're going to beat the Lunar Lander environment in under 150 lines of code. It's going to be easier than you think, and you're going to see how easy right now. So Keras has a number of imports. We want to import the dense and activation layers to handle the fully connected as well as the activation functions. From keras.models, we are going to want to import the sequential, which is what we're going to use to actually build the model, as well as the load model function, and that will facilitate saving and, well, loading models anyway. We're also going to need the Atom Optimizer. We will also need NumPy for NumPy type operations. That is it for imports. So we're going to have to start out with a number of classes, the first of which being the replay buffer for the agent. So the replay buffer handles storage of the state, action, reward, and state transition tuples, as well as the done flags from the environment, so that the agent can use these transitions to learn about the parameter space of the problem. You may have seen this in other videos. If not, that's okay. There are a number of ways to implement this. I'm going to use NumPy arrays. That's just my preference. If you know of another way, say using a Python deque, that is perfectly acceptable as well. So I have a number of parameters here. The max size will determine the maximum size of the memory. The input shape is just the input shape of the environment. So in the case of Lunar Lander, it's a vector of 8 elements. I have this other variable here called discrete. Now this is to incorporate some element of extensibility into our class. So if we are dealing with a discrete action space, meaning that the action can be an integer set of values, then we're going to want to use a one-hot representation, one-hot encoding of our action space. Whereas if we're using this replay buffer for something like deep deterministic policy gradients, then we don't want to do that. So we'll just store the actions as a vector. And so we want a way of determining which way we're going to store them. That's the purpose of the discrete flag. So next up we have our state memory, and this will take the states from the environment and store them. There's also a new state memory, which has identical shape, as you might imagine, and the purpose of this is to keep track of the new states we get after taking an action. We're also going to need a data type, and the reason is that if we are doing a one-hot encoding, then we don't want to save the numbers as floating point integers. We want to save them as not as floating point numbers, we want to save them as integers. So if it's discrete, then we're going to save it as a numpy int 8. Otherwise, we'll save it as a numpy float 32. So that's pretty straightforward. And in any event, the action memory is an array of shape self.memsize by number of actions. And you know what? Actually, I don't need to save the input shape here, so let's get rid of that. Next, we need the reward memory, and that is just an array of shape mem size. That'll just keep track of the rewards the agent receives from the environment. And we also have a terminal memory. So what this keeps track of is the terminal flags from the environment, because when we transition into the final state, the terminal state, when the episode is over, we don't want to take into account the reward at the next state. This will become more apparent when we get to the learning function, when we calculate the target values for Q. But basically, once the episode is over, you don't want to take into account the reward from the next state, because that is a reward from another episode. So we need a way of accommodating that, and that is what the terminal memory is for. The store transition function is just a way of storing the state, action, reward, new state, and done flags in our memory. The first thing we want to know is what is the first available memory. That is given by mem counter modulus mem size. The reason it's a modulus is because the mem counter is just going to run. It's just going to increment by 1 every time we save a memory, whereas the memory size has a finite size. So let's say we have 1,000,000 spaces. Once we hit that 999,999 element, once we add a memory to that, we want to go all the way back around to the beginning of the array at position 0, and that's accommodated by the modulus operator. So the state memory add position index is just the state that you're passing in. The new state memory at the index is the new state, as you might imagine. The reward memory at position index gets the reward. The terminal memory at the index position does not get the done flag. It is 1 minus int of done. And the reason for that is that the done flag is false when the episode isn't over. And so if you just save it as the integer representation of true or false, then you will end up with the exact opposite behavior of what you want. So you want 1 minus done, so that way when the episode is done, you get 1 minus true or 0. A little bit convoluted, but it is absolutely necessary to do that way. You get the wrong answer if you do not. So it's an easy mistake to make. Next up, we have to deal with the actions. So in the case of a discrete action space, we want to get the one-hot encoding of our action. So the action is some number 0, 1, 2, 3, or 4, for instance. And so we want to translate that into a vector of either 0, 1, 0, 0 for action 1, for instance, 0, 0, 0, 0 for action 0, 0, 0, 1 for action 2, and so on and so forth. Easiest way to do that is to make a NumPy array of zeros in the shape of the action memory's first dimension, and the index that by the action and set that equal to 1.0. Everything else is equal to 0, so that is a one-hot encoding. And then just say action memory subindex equals actions. Otherwise, you want to say self.action memory subindex equals action. Pretty straightforward. Final thing you want to do is increment your memory counter every time you add a memory. Very important, otherwise you just keep overriding the last step. Not very helpful. So that stores every transition we do from the environment. Next, we need a function to sample a subset of the memory. And that'll take a batch size as input because you don't want to sample the entirety of the memory. You'd be feeding a million memories through your network. That's kind of slow. You just want to feed some fixed batch size. We could even set batch size to be a member variable. In fact, yeah, no, we'll just leave it like this, whatever. It doesn't really matter. I'm always looking for ways to improve, but sometimes it's really not worth the trouble. So the first thing you need to know is what is the maximum memory you have written to. So that way you can sample up to that. It could be memcounter, or if memcounter has gone past the end of the maximum memory, then the maximum element is just the mem size, because you don't want to read beyond the end of the array. While that is safe to do in Python, it won't, it won't bite you in the rear end like in C with undefined behavior, but it will break the software at the worst possible time. So it is a minimum of either self.memCounter or self.memSize, not the max, the minimum. And next you want a random batch of that memory all the way up to the maximum memory in the shape of batch size. Then all you have to do is access those subarrays of your memories by saying states equals self.state memory subbatch, and states underscore new state memory batch, and so on and so forth. Rewards self.reward memory batch, actions self.action memory subbatch, and terminal self.terminal memory subbatch. I misspelled terminal. That's a problem. And then you just want to return those values. Return states, actions, rewards, new states, and the terminal flags. And that is all we need for our replay buffer. If you've seen some of my other videos, then I may have stuck this in the agent class. More recently, I've begun sticking this in its own particular class so that we can reuse it for other environments. I'm going to eventually package all this up into maybe like a library or a package or something so that people can just kind of pull agents from my GitHub. In any event, now we move on to the function to build our DeepQ network. And we don't need a class for this. I suppose you could use one, but a function works just as well. And so we take learning rate, number of actions, input dims, the first fully connected layer's dimensions, and the number of dimensions for the second fully connected layer. So building models in Keras is actually pretty straightforward. We can use the sequential object to construct a sequence of layers, and it takes a list of inputs, the first of which being a dense layer that takes FC1 dims as output, with an input shape of input dims, comma. And the input dims, comma allows us to either pass in a batch or a single memory. That will be important when we are learning or choosing an action respectively. Next, we need to do an activation, and that will be a ReLU. We'll also need a second dense layer that just takes FC2 dims, and we don't have to specify an input shape because it's inferred. That's one of the really nice things about Keras, is that in regular TensorFlow you have to specify the input shapes, whereas here you don't. It's kind of nice. I really like it. And we need another ReLU activation, and we have another layer finally which just takes an actions. And that is it for our full DeepQ model. Now all we have to do then is compile the model, and that will take an optimizer argument, which will be Atom with a learning rate specified by learning rate, and the loss is just going to be a mean squared error. And then we want to return the model. And this will allow us to call model, I think it's .fit and model.predict to handle training and choosing actions respectively, which is very, very nice. This is very simple with respect to even PyTorch, where you have to define a feedforward function. This knows automatically what to do once you build the graph. Very, very nice. Next up, we have the agent class, and that is just derived from the base object. The constructor takes a whole boatload of arguments, alpha for learning rate, gamma. Gamma is our discount factor. It is what tells the agent by how much to discount future rewards. So when you take into account the reward for the next step, you multiply it by gamma to reduce the contribution to the overall target. We also need a number of actions. Oh, and it's between 0 and 1, and typically something like 0.99, 0.95, something like that. Epsilon is a random factor, so if we draw a random number and it is less than epsilon, we take a random action. Otherwise, we take a greedy action, meaning the best known action given we're in some state. This is known as the explore-exploit dilemma, and epsilon greedy is one well-accepted, well-used solution to it. It's quite straightforward. A batch size, input dims, a factor by which to decrement epsilon. That's not super important in the Lunar Lander environment because it's simple, but if you want to use this type of network in something like, say, the Atari library, you're going to want to decrease epsilon slowly over time, so this epsilon decrement factor would have to be much closer to 1. As it is, it's going to make it through 5 or 10 episodes before it's all the way down to the epsilon end, which is the minimum value for epsilon. So you never want to set epsilon, well, I mean, if you want to evaluate the model, you of course set epsilon to 0, but if you are training, you want to leave epsilon finite, so that way the agent is always, some proportion of the time testing its model of the world, because you never know if your idea of the greedy action is actually the true greedy action. So you always want to be exploring when you're training. And we're also going to need a file name for saving our model. That's just a string. We'll call it dqnmodel.h5. Pretty straightforward. First thing we're going to need is our action space. This is the set of available actions. It's just a list comprehension that gives us the range of integers up to number of actions. This will be used when we want to select a random action. We also want number of actions. I want to save our gamma, our epsilon. We want the epsilon decrement. We want the epsilon minimum. That's epsilon end. We also want the batch size and a model file as fname. We also need a memory. That's the point of having the replay buffer. That gets a mem size, input dims, and actions, and discrete equals true as arguments. Let's put that on the next line. Because remember, the Lunar Lander environment is a discrete action space, so we want to pass in the discrete flag as true. We also want a Q network for evaluating our actions. So that's just going to be build dqn. We're going to pass in alpha for learning rate, number of actions, input dims, and for default sizes we'll just use 256 by 256. Through experimentation I've found that to work reasonably well. There may be better values out there. You can play around with this, pull it from my GitHub, clone it, and see what you can do, see if you can beat my performance. That would be excellent. Next, we need a way of interfacing with our memory to save new state transitions, and we'll call that the remember function. That'll take a state, action, reward, new state, and done as input. Self.memory.store transition, state, action, reward, new state, and done. That's just an interface function. It's a little kludgy, but it's kind of the price you pay for using object-oriented programming. Sometimes you get stuff that looks kind of funny. We need a function to choose an action, and that takes the state as input. So remember when I said that the function up here has the input dims comma blank to accommodate batch size. So this expects something that has shape either input dims by 1 or input dims by some unknown number. And what we have in state is something that is shape input dims, so we actually have to reshape it by calling numpy new axis. This will just add an axis to the vector, so that way we can use it in our feed forward. Next, we need a random number, and if rand is less than self.epsilon, action equals np random choice self.action space. Otherwise, if you want a greedy action, then you have to do a feed forward qeval.predict, not predict day, predict state, and say action equals numpy argmax actions. So this will pass the state through the network, get the value of all the actions for that particular state, and select the action that has the maximum value. It'll take a greedy action, in other words. And when you're done, just return that action. Now that I'm looking at this, we don't need to save up here the number of actions because we have the action space, and we just pass in n actions here. So we don't need to save that variable. We can clean it up as we go along. That is perfectly allowed. Now we come to the most interesting function in the entire class, the learning function. So right away we have a small dilemma. So the agent, this is a temporal difference learning method. That means it learns on every step. That's what temporal difference means. You take the delta between different states and learn on each step. So the question becomes, we have instantiated our memory with a bunch of zeros. So do we fill up that memory with random gameplay before we actually start learning? Or do we just start learning and live with the fact that we have arrays of numpy zeros? I'm going to opt for the latter case, but the consequence of that is that we have to wait until we fill up batch size of our memory before we start learning, because you don't want to learn from, in the case of no actions, you don't want to learn from, you know, a bunch of zeros, and you certainly don't want to learn by using a single state or 2 states or 3 states or whatever. So you want to learn at least with the number of batch size states. So if self.memory memory.mem counter is less than self.batch size, return. Otherwise, if you haven't returned, then you can go ahead and start the learning process. First thing you want to do is state action reward new state and done equals self.memory.sample buffer self.batch size. And we can kind of tab that over. So that gives us all of our stuff from the state transitions in shape batch size. And we are dealing with a one-hot encoding here. So we want to go back from a one-hot encoding and say action values is numpy array, action space, type numpy int 8, and action indices, that is the index of the action we took. We want to go back from a one-hot encoding to a integer encoding. That's just numpy dot action and action values. Next, you want to feed the set of states through the model and calculate the value of the current states as well as the next states. Predict new state. And then we want to take a QTarget QEval.copy. I'll show you why in a second. And for our array indexing, we're going to need a batch index. This is actually a point of contention on my GitHub. I should address that issue. Some people have proposed some changes that I don't think are correct. This is the way to do it. They get some type of wonky dimensional mismatches. I'll have to take a look at their code. But anyway, you want to address all of the states in the particular batch that you have, but you can't just use regular old array slicing, otherwise you end up with something of shape batch size by batch size, which won't trigger an error in the calculation because it's square. When it does the mean squared error, it just reduces it down, but it gives you the wrong answer and you don't actually get learning. So it's a pretty simple mistake to make, but it is a mistake nonetheless. So it's batch index, action indices. So the batch index is just 0 up to batch size minus 1, and action indices is the integer representation of the action we took. So we took action 0, 1, 2, or 3. It is a 0, 1, 2, or 3 instead of a one-hot encoding of that. Reward plus self.gamma times numpy max q next axis equals 1 times done. So reward is the reward the agent received on each step. Gamma is our discount factor, and numpy max is the maximum action for the next state. So it's the best possible reward you could have received in the next state. That's why we have axis equal 1 multiplied by the done flag. This is the update equation for the, or part of the update equation. This is our target. This is what we're going to use in our loss calculation. So next, we want to actually perform the fit and pass in the states and the QTarget, and we want to set verbose equals 0, and that's because by default Keras will spit out the accuracy and stuff as you go along, which in this context really doesn't mean much, and we're going to be executing many learning operations, so it's just going to clutter up the terminal. So we set verbose to 0 to suppress the output. This actually does the fitting. So what it does is it passes the states, set of states, the batch of states through the network, calculates their values based on the current estimate, and then compares those to QTarget. QTarget is like what we're shooting for. It's kind of like the current. It is the current reward plus the best possible action for the next state. It's kind of like the delta between where we want to be and where we are, and it'll use those two quantities for our loss. Finally, we need to handle the epsilon. So you don't want epsilon to stay large for the entire episode or entire set of games. So it's self.epsilon times epsilon decrement if epsilon is greater than, sorry, I need a break there, greater than self.epsilon min, else set it equal to epsilon min. So this will decrement epsilon over time until it is equal to epsilon min, and then leave it there. And that is how we learn. So just to recap, sample your buffer. It's worth noting that this sampling is in general going to be non-sequential memories. You don't want to sample sequential memories because this results in correlations in the learning that gets you kind of hung up in one or two spots in parameter space and slows down the learning process. So you want to sample non-sequential memories from a vast array of games, ideally. And then we have to go back from the one-hot encoding to the integer encoding, calculate the value of the current states and next states, and then go ahead and update the QTargets based on the maximum values of the next state, and then use the QTarget as the target for the loss function for the Q network. Finally, we come to two functions called save model. That will just call self.qeval.save on model file, and we want to load model, and that just calls sets qeval equal to load model self.model file. And of course, load model is imported from keras.models. And that is it for the DeepQ network. Very, very straightforward. About 110 lines or so, not counting white space, a little bit less. So let's go ahead and go to the main function and test this out. So first thing we want to do is import the model from simple DQN Keras import agent, and we're going to need numpy as np. We're going to import my fancy schmancy plot learning function to generate the learning plot you saw at the top of the video. We are also going to need gym right here, import gym. And what else do we need? That is it for imports. So if name is main, be helpful if I could type today. Gym.make lunar lander v2. We're going to run for 500 games and instantiate our agent with a gamma of 0.99, epsilon of 1.0 to start out so that it takes purely random actions for the first few steps, and alpha of learning rate of 0.005. Input dimensions for this problem are 8. It's a vector of 8 elements. There are 4 actions. The mem size is 1 million. Batch size of 64, and our epsilon end is 0.01. So if you already have a model.saved, you would call agent.loadModel right there. You have to call the load model after instantiating the agent, of course. Next up, we'll have an array to store our scores, an array to store the values of epsilon over time. And now we can start playing our games. For I in range and games, done is false. Score starts out as 0. While not, we have to reset our environment, of course. Can't forget that. Observation equals env.reset, and say while not done. The first thing you want to do is to choose an action equals agent.choose action, and that, of course, takes the observation as input. You want to decide what to do based on the current state. We're going to take that action, receive our new state, reward, done, and info, env.step action, and we want to keep track of our reward as well as that transition. So agent.remember, state, action, reward. Sorry, it's observation, action, reward, observation underscore, and done. And then we want to set the current state to the new state and call our learn function. At the end of every episode, you want to append the epsilon from the agent. I guess you could do it within the episode, wouldn't hurt anything. Scores out append score. And every game we're going to print out the running average of the last 100, and the reason is that the metric for having solved the environment is getting a average score of over 200 for the last 100 games. So it's np.mean scores max of 0 or I minus 100 all the way up to I plus 1, and print episode I score to F percent score average score %.2f percent average score. And if I modulus 10 is 0 and I is greater than 0, we're going to want to save our model. And at the end, say x equals I plus 1 for I in range and games. This will give us the x-axis for our plot learning function. Plot learning, x scores, epsilon history, and file name, which I forgot to set. Leonard.png. Okay, so that looks like everything. Let's head to the terminal and see if I made any typos. All right, here we are. Python main Keras. Name epsilon n is not defined in my constructor. Okay, let's fix that. So that is on line 63 in the init. Eps end, it is because it is epsilon end. Did I call it epsilon end here? I did. Very good. Let's head back to the terminal and try it again. One more time. Replay buffer has no attribute mem counter. Well, it should. All right, let's head back and add that. All right, that is in line, or rather up here. Self.mem counter equals 0. I could have sworn I had that, but obviously not. All righty. One mo again. It says arrays used as indices must be of integer or Boolean type. Oh, really? So did I not? Let's head back to the code editor and see what I forgot. Okay, so I see the problem. It says arrays used as indices must be of integer or Boolean type. So up here in the action memory, I forgot something very fundamental. dtype equals dtype. That's why I have the dtype in there. That's the disadvantage of making videos late at night. You're pretty tired. So, okay, let's go back to the terminal and see what else I screwed up. Once again. Perfect. It is running. So, I'll let that run for a minute as I ramble on, but you can already see at the beginning of the video how the performance did. It managed to get a score well over 200, something like 270. I let this run quite a while. Let's see if I can I scroll up? No, must be a new window. But you can already see the score start to improve over time. The agent is learning. Right now the epsilon should be about 0.01. The epsilon decrement takes it quickly down from 1.0 all the way down to 0.01 within just a few episodes. So we've effectively, or rather we will effectively beat the environment, saving it every 10 games, so that way we can, you can do some straight up evaluation if you want to see how it does without random actions. But yeah, this is a relatively straightforward implementation of deep Q learning in Keras. Ways to improve this would be to add in a second deep Q network to handle the calculation of the target values and then one of them to calculate the actions. In other words, double deep Q learning. That's a significant advancement on the algorithm. For this simple environment, it doesn't really matter, but if you want to tackle things from the OpenAI gym, like the Atari library, then you're going to need the double deep Q learning. But that is it in a nutshell. It only took, half an hour or so and about 110, 120 lines of code, 150 at most. Very, very simple. If you found this helpful, make sure to share. It helps me get found. It's free, doesn't cost you anything. Subscribe, hit that bell icon, leave a comment, question, suggestion down below, and I'll see you all in the next video.